Hey everyone, and welcome back to the Deep Dive. Today we are going to be tackling a topic that's, well, it's a pretty huge one. It's the expanding universe.
hmm
And
Yeah, that's one way to put it.
we've got some excerpts from this book, and it is dense. It is filled with equations, cosmological jargon.
It is a bit much.
But that's why you're here, right? To help us make sense of it all.
That's the plan. We'll break it down, make sure we understand those key takeaways, and hopefully by the end of this deep dive, you'll have a whole new perspective on our place in the cosmos.
I like it. A journey through space and time. Where do we even begin with something as vast as the expanding universe?
Well, one of the fundamental principles in cosmology, and really like the foundation for a lot of what we'll talk about, is this idea that the universe is homogeneous and isotropic on large scales.
Okay, hold on. Back up for a sec. In plain English, for those of us who don't speak cosmologist,
Mhm.
what does that actually mean?
Okay, so imagine you could zoom out way beyond our galaxy and look at the universe from a really distant vantage point. This cosmological principle basically suggests that no matter where you look in any direction, the universe would look pretty much the same.
So it's like if you were standing in the middle of the ocean, no matter which way you turned, you just see water.
Exactly. And for a long time, this is just an assumption, a kind of wild guess by physicists. But then towards the end of the 20th century, data started coming in that actually confirmed this homogeneity.
Wait, so they just assumed the universe was the same everywhere? That seems like a pretty big leap of faith.
It might seem that way, but think about it. If the universe had like drastically different properties in different regions, it would be pretty hard to explain why our little corner of it seems so average, you know?
Hmm. Yeah, that's a good point. It still seems pretty mind-boggling, though, to think that everything we can see, all the stars and galaxies, are just a tiny part of this uniform cosmic tapestry.
It really is. And here's where things get even more interesting. While the universe is homogeneous on large scales, we know it's not perfectly smooth, right?
Hmm.
We've got galaxies, clusters of galaxies, even larger structures.
So it's like looking at a forest from a distance. From far away, it looks like a solid mass of green.
Oh.
But up close, you see all the individual trees and the variations in the landscape.
A perfect analogy. And that actually brings up some really intriguing questions. If the universe started out as a hot, dense soup of particles, how did these large-scale structures even form? How did we go from uniformity to the incredible diversity we see around us?
Okay, now I'm hooked. So how did this all happen?
Well, that brings us to another fundamental fact about the universe. It's expanding.
Right. We've all heard about the Big Bang and the expanding universe. But what does that actually mean? Like, is it an explosion that sent everything flying outward?
Not exactly. It's not like an explosion in the traditional sense. Think of it more like imagine dots on the surface of a balloon. As you inflate the balloon, the dots move farther apart, not because they're moving across the surface, but because the surface itself is stretching.
So the galaxies aren't flying through space. The space between them is actually growing. That's kind of mind-bending.
It is, and what's even cooler is that this expansion looks the same from any point in the universe. There's no center of the expansion. If you were on a different galaxy billions of light years away, you'd still see all the other galaxies moving away from you as if you were the center.
Whoa, that's wild. It really challenges our Earth-centric perspective. So if everything is moving apart, how do we even know the universe is expanding? How do we measure this cosmic stretching?
That's where the Hubble constant comes in. It tells us how fast the universe is expanding right now.
Okay, so how do we measure this Hubble constant? Are we talking giant cosmic rulers here?
Not quite. We use what are called standard candles.
Standard candles.
They're objects in space, like certain types of stars or supernovae, that have a known luminosity. We can measure how bright they appear from Earth, and by comparing that to how bright we know they actually are, we can figure out how far away they are.
So it's like knowing the wattage of a light bulb and judging how far away it is based on how dim it appears.
Exactly. And once we know the distance to a galaxy and how fast it's moving away from us, we can calculate the expansion rate of the universe.
Okay, that makes sense.
Hmm.
Now here's a thought. If we know how fast the universe is expanding now, can we rewind the clock and figure out how old it is?
Absolutely. If we know the speed and the distance, we can estimate how long it took for things to get where they are now. Think of it like knowing your current speed and how far you've traveled on a road trip. You can roughly calculate how long you've been driving.
So how old is the universe according to these calculations?
By using the Hubble constant, we get an age of roughly 15 billion years. Now, that's just a rough estimate. The actual calculation is more complex, involves things like the universe's composition and curvature.
Still, 15 billion years. That's a number that's almost impossible to even grasp.
It is. And to really understand how we arrived at that number and what it means for the universe's evolution, we need to delve into the world of Einstein's general relativity.
Ah, yes. Here's where things get really interesting. Einstein's theories always seem to take us down the rabbit hole.
They do. You see, in general relativity, gravity isn't just a force, it's a manifestation of the curvature of space-time itself.
Hold on, I'm trying to visualize this. So you're saying that massive objects like stars and galaxies actually warp the fabric of space and time around them.
Exactly. And this warping is what we experience as gravity. So it's not just that objects are moving through space, but space itself is dynamic and can be warped and stretched by the matter and energy it contains.
Okay, my brain is starting to hurt, but in a good way. So how does this tie into the expanding universe?
Well, if we want to understand how the universe evolves on a grand scale, we need to use general relativity because it can handle things like matter moving at incredibly high speeds and the intense gravitational fields that were present in the early universe.
So Newtonian physics was a good starting point, but to really understand the big picture, we need Einstein's more sophisticated tools.
You got it. Newtonian physics is like a bicycle, while general relativity is like a spaceship. Both can get you places, but the spaceship can take you much farther and explore much more extreme environments.
I like that analogy. So with Einstein's spaceship, we can explore things like the shape of the universe, right?
Precisely.
And is the universe shaped like a sphere? Or is it flat, like a pancake? Or
Yep.
something else entirely? I'm genuinely curious.
That's one of the big questions in cosmology, and the answer is more complex than you might think. Let me explain. So, in a homogeneous and isotropic universe, there are three possible geometries, kind of like a flat sheet, a sphere, or a saddle. Just imagine those shapes, but in 3 dimensions.
Okay, I'm picturing those shapes. A flat sheet extending infinitely in all directions, a sphere that's finite but has no edges, and a saddle that's curved somehow. But which one is our universe?
Well, that's what we're trying to figure out, and it all depends on something called the cosmological parameter, or omega. Think of it like a cosmic recipe. The ingredients are matter, energy, and this mysterious thing called the cosmological constant.
Cosmological constant. That sounds intriguing.
It is. It's basically a kind of anti-gravity, a force that's pushing everything apart, counteracting the pull of gravity from all the matter in the universe.
So we've got this cosmic tug of war going on. Gravity's pulling things together, and the cosmological constant is pushing them apart.
Exactly. And the relative proportions of these ingredients represented by omega determine the shape of the universe. If omega is greater than 1, the universe is closed like a sphere. Less than 1 means it's open like a saddle. And if omega is exactly 1, the universe is flat, extending infinitely like that sheet we talked about.
So what's the latest scoop? What do you scientists think our universe's shape is based on this omega value?
Based on the most recent observations, it seems like the universe is remarkably close to being flat.
Really? So it's like that infinite sheet stretching out forever?
It seems that way. But here's the thing. Knowing the shape also tells us something about the universe's ultimate fate.
Okay, now this is where I get really curious. What are the possible scenarios for the end of the universe? Does it just keep expanding forever? Or is there some grand finale?
There are a few possibilities, and they all hinge on this cosmic balancing act between gravity and the cosmological constant. One possibility is that if the cosmological constant is positive and strong enough, the expansion of the universe will just keep accelerating, leading to a big freeze.
A big freeze. That sounds kind of lonely.
It does, doesn't it? Basically, in this scenario, the universe just becomes increasingly cold and empty as galaxies drift farther and further apart. Eventually, stars would burn out, black holes would evaporate, and the universe would become a vast, dark, and desolate place.
Okay, that's a bit depressing.
Yep.
Any other more cheerful possibilities?
Well, there is. If the density of matter and energy in the universe is high enough, gravity might eventually win out over the cosmological constant. This would cause the expansion to slow down and eventually reverse.
So instead of a big freeze, we get a big crunch. Everything collapses back in on itself.
Exactly. In this scenario, the universe would contract, becoming hotter and denser until everything collapses back into a single point, like a reverse Big Bang.
That's certainly more dramatic than a slow fade out. But it's hard to imagine everything we know being crushed into oblivion.
It is. And there's even a third possibility, a kind of middle ground between the big freeze and the big crunch. If the cosmological constant and the density of matter and energy are perfectly balanced, the expansion would slow down but never quite stop.
So a kind of eternal coasting.
You could say that, but here's where things get even more interesting. To illustrate some of these concepts, cosmologists have come up with some theoretical models of the universe. One of them is the Milne universe.
Milne universe. That sounds like something out of a science fiction novel. Tell me more.
It's a purely hypothetical model, but it serves as a really useful thought experiment. Imagine a universe with no matter at all, just empty space expanding according to special relativity.
Empty space. That doesn't sound very exciting.
It might not sound exciting, but it helps us understand something really crucial about the way we perceive expansion in the universe. You see, even in this completely empty universe, if we use a specific coordinate system, it would look like galaxies are moving apart, just like in our universe.
Wait, so you're telling me that we could observe expansion even if there was nothing there to expand?
That's the key insight of the Milne universe. It shows us that the way we measure distances and velocities in an expanding universe can create an illusion of movement. It highlights the importance of understanding the coordinate systems we use in cosmology. It's all about perspective.
Okay, I think I'm starting to get it. The Milne universe is like a cosmic trick of the eye. It helps us remember that things aren't always as they appear, especially when we're dealing with the vastness of space and time.
Exactly. It's a good reminder that our observations are shaped by our perspective and the tools we use to measure the universe. Now, another important model is the de Sitter universe. This one's a bit more complex, but it's crucial for understanding inflation, that period of exponential expansion in the very early universe.
Right, we touched on inflation earlier. It's like the universe went through a massive growth spurt right after the Big Bang, right?
Exactly. Imagine the universe in its infancy, incredibly hot and dense. Then for a tiny fraction of a second, it expanded exponentially, growing by an enormous factor in an incredibly short amount of time.
That sounds dramatic. But what could possibly cause such rapid expansion?
That's one of the big questions, but the de Sitter universe gives us some clues. This model is unique because it's homogeneous and isotropic not only in space, but also in time. It's like the ultimate in cosmic symmetry.
Okay, so everything looks the same everywhere and at every point in time.
Exactly. And this symmetry has some interesting consequences. For example, the de Sitter universe can be described using different coordinate systems, and depending on which one you choose, it can appear to have different shapes.
Wait a minute. How can the same universe have different shapes depending on how you look at it? That's confusing.
It's a bit like looking at a globe versus a flat map. Both represent the Earth, but they use different projections and distort distances and shapes in different ways. In the de Sitter universe, the shape you perceive depends on the chosen coordinate system, not an inherent property of the universe itself.
Okay, so the shape is more about our perspective
Yeah.
than some absolute truth. But how does this relate to inflation?
Well, a pure de Sitter universe is static. It doesn't actually expand. But by introducing a slight wobble, a little bit of asymmetry, we can get a model of exponential expansion, which is what we believe happened during inflation.
So inflation is like a de Sitter universe with a bit of a twist.
That's a great way to put it. And the leading theory is that this twist is caused by a hypothetical field called the inflaton. This field is thought to have had a very specific energy profile that drove the rapid expansion of the universe during inflation.
So the inflated field is like the fuel for this cosmic growth spurt.
Yeah.
And once the fuel runs out, inflation stops.
Exactly. Inflation ends, and the universe settles into a more gradual expansion, which is what we observe today.
This is all incredibly fascinating.
Yeah.
But how do we know that inflation actually happened? Is there any evidence for it?
There is. One of the most compelling pieces of evidence comes from the cosmic microwave background radiation, or CMB.
CMB. That rings a bell.
It's like a baby picture of the universe, a snapshot of what it looked like about 380,000 years after the Big Bang. It's a faint glow of radiation that permeates all of space, and it's full of information about the early universe.
So we can actually see remnants of the Big Bang.
We can. And what's amazing is that the CMB is incredibly uniform, just like the cosmological principle predicts. It suggests the early universe was incredibly smooth and homogeneous.
But wait, didn't you say earlier that the universe isn't perfectly smooth? We've got galaxies and clusters and all sorts of structures. How did those form if everything started out so uniform?
That's the beauty of it. While the CMB is incredibly uniform overall, it contains tiny temperature fluctuations, variations on the order of 1 part in 100,000.
So it's not perfectly smooth after all.
No, and those tiny imperfections are actually incredibly important. They're the seeds from which galaxies and clusters eventually grew. Inflation provides a mechanism for generating these fluctuations, stretching tiny quantum fluctuations into these large-scale cosmic structures.
So those minuscule temperature differences in the CMB are like the blueprints for the universe we see today.
Exactly. It's like looking at a faint map of the early universe, where the slightly warmer spots represent regions of slightly higher density. Over billions of years, gravity pulled matter towards those denser regions, forming the galaxies and clusters we see today.
That's incredible. So the CMB not only provides evidence for inflation, but it also shows us the initial conditions that led to the formation of all the structures in the universe.
That's right. And the patterns of these fluctuations align remarkably well with the predictions of inflationary theory.
Wow, it seems like inflation solves a lot of cosmological puzzles.
Yeah.
It explains the universe's homogeneity, the existence of these tiny fluctuations that seeded cosmic structures, and even helps us understand why the universe is so close to being flat.
It does. Inflation has become a cornerstone of modern cosmology, providing a framework for understanding the universe's earliest moments and the processes that shaped its evolution. But remember, we're still piecing together this cosmic puzzle, and there's a lot more to explore.
This is all so mind-blowing, but I feel like we've only scratched the surface.
We have. But for now, let's take a moment to reflect on what we've learned. The universe is expanding. Its shape is intimately tied to its composition and the mysterious cosmological constant, and it all started with a bang and then a rapid burst of inflation that shaped the universe we see today.
Welcome back to the deep dive. It feels like we've traveled billions of years across the universe already.
I know, right? It's been quite a journey.
We've covered so much from the Big Bang to the CMB, that cosmic microwave background radiation.
And all those theoretical models like the Milne universe and the De Sitter universe.
Yeah, those were really helpful for wrapping my head around some of these mind-bending concepts. I especially like the Milne universe analogy, how even an empty universe could appear to be expanding, just depending on how you look at it.
It's a great illustration of how our perspective and the tools we use can shape our understanding of the cosmos.
Okay, so we've talked a lot about the past, but what about the future? What's in store for this ever-expanding universe of ours?
That's the big question, isn't it? The ultimate fate of the universe. It's one of the biggest mysteries in cosmology.
So what are the leading theories out there? Is it the big freeze where everything just keeps spreading out until it's cold and dark? Or is there a chance for a more dramatic ending?
Well, as we discussed earlier, the most likely scenario based on current observations is indeed the big freeze.
Kind of a bleak outlook.
It does paint a picture of a universe slowly winding down. But remember, we're talking about timescales that are almost impossible to comprehend.
Billions upon billions of years in the future.
Exactly. And who knows what incredible scientific advances might happen between now and then. Our understanding of the universe is constantly evolving.
That's true. What we consider facts today might be completely different in the future.
Absolutely. But based on our current knowledge, the big freeze seems to be the most plausible outcome.
So galaxies drift farther and farther apart, stars eventually burn out, and the universe becomes this vast and empty place.
That's the general idea. But there are other possibilities, too. Some theories suggest that dark energy, the mysterious force driving the accelerated expansion, might not be constant.
So you're saying dark energy could change its behavior over time.
Exactly. It could increase or decrease, which would have a dramatic impact on the universe's fate.
So if dark energy weakens, maybe gravity could take over and lead to the big crunch scenario.
That's one possibility. Or maybe dark energy could become even stronger, leading to an even more rapid expansion, a scenario sometimes called the Big Rip.
Big rip. That sounds intense.
It is. In this scenario, the expansion becomes so powerful that it eventually tears apart everything, galaxies, stars, even atoms themselves.
Wow, that's a pretty dramatic ending to our story.
It is. But remember, these are all just theoretical possibilities based on our current understanding of the universe. The actual fate of the universe is still an open question.
So what you're saying is there's still a lot we don't know, and the universe could have some surprises in store for us.
Exactly. That's what makes cosmology so exciting. There's always something new to discover, and our understanding of the universe is constantly evolving.
I guess that's a good reminder to stay curious and keep exploring.
Absolutely. And who knows, maybe one day we'll have the answers to some of these big cosmological questions.
Well, this deep dive has certainly given me a lot to think about. We've explored the expanding universe, delved into the mysteries of dark matter and dark energy, and even pondered the universe's ultimate fate.
It's been quite a journey. And I hope our listeners are leaving with a sense of wonder and maybe a few more questions than they started with.
I think it's safe to say that if you're anything like me, you're probably looking up at the night sky with a whole new perspective.
And that's what it's all about, isn't it? recognizing our place in this vast and incredible universe, and never losing that curiosity to explore its mysteries.
Well said. Thanks for joining us on this deep dive, everyone. And remember, keep looking up, keep asking questions, and never stop exploring.
Until next time.